Let's start. My name is Vitaly Khudobakhshov. I'm from St. Petersburg State University, Russia, and I would like to talk about metacomputations and its application to artificial general intelligence. The first few words should be about the motivation of my work. It's quite easy to describe it in my particular case. I'm lazy, and I don't want to write a huge amount of code to achieve AGI. In this case, if you love programming and you are true AGI believer as me, then you have two main opportunities. First of all, to write programs in Haskell, because programs in Haskell are short enough to lazy guy, or to write programs which can write other programs for you. Of course, these choices are not completely disjoint, but this talk is about programs which manipulate other programs. Such programs are called meta-programs, and computations which involve other programs as data and probably result are called metacomputation as well. Due to time pressure, I will focus in my talk only on probably the most simple method of metacomputation, but it's powerful enough for our purposes, at least in theory. This method called partial evaluation or specialization. Suppose we have a program P with two or more arguments, when the specializer is defined as follows. Everyone can think about this specializer as a program which gets a two-argument program and returns one-argument program as a result. But output program behaves for any particular y in the same way as the input program with fixed first argument x. Of course, partial evaluation can be done with respect to second argument as well. The most important thing is that a specializer makes a deep transformation which reduces the source program to an efficient one. This means that this inequality holds. I would like to get a very simple example of such deep transformation, but we don't have time to describe all process, and I will focus on the resulting program, skipping almost all details. That's how it works. This is the power function implemented in the toy, but during complete flowchart language. This is the arguments, its entry point, and labels with block of code. It's easy to understand that program does. If we want to specialize our program for second argument, for example, to particular value, we need to do two things. First, substitute the value for variable n, and this is the main thing. Remove all unnecessary steps according to our assumption. As a result, we have a reduced program. It's very simple to understand what the program does. It's very easy. You can see that almost all unnecessary steps was removed, but we can do more. Of course, it's pretty simple. Why it makes sense in AGI? To understand this, we need to look at a very beautiful result obtained independently by Turchin and Futamura in the 70s. It's called Futamura projections. It sounds obvious, but it has many important applications. Futamura found that if specializer is written in the same language as well as programs it specialize, then we can apply it to itself. Let's start from definition of interpreter. They can create first Futamura projection, but applying specializer to interpreter. Suppose we have initially a program written in language L, and interpreter written in language R. After specialization, we will have a compilation result from language L to R. Second projection gives us a compiler from L to R, and the next step leads us to compiler generator. It's very easy, really, but it's leads us to very interesting consequences. For example, let's try to apply this technique to a wide range of programs, not necessary to interpreter. Suppose we have some intelligent program called PRED, which maps two arguments, empirical knowledge and wall state, to another wall state. It's called predictor. After applying specializer, we will have following equation, where result of specialization can be considered as a model, because M is a double-to-double function. Second projection will give us a model generator, but more interesting observation is that a generator of generators is the same thing as a compiler generator. You can see that we can extend Futamura result to a wider range of programs. But the most interesting result is related to relationship between narrow and general intelligence in terms of metacomputations. Here I skipped additional arguments in AGI system as well as in narrow intelligence for keeping things simple. Consider the following equation. It's a relation between general system and narrow intelligence. Here PD is problem description. It is pretty interesting because according to the equation we can obtain for example, okay, suppose we have a general game playing software, and we have formal description of game of chess. According to this equation, we can obtain optimized chess program by using specialization. This means that we do not interested in how fast our general program works. It may be too general or too slow, but it doesn't matter because we are interested in how fast specialization and narrow intelligence work together. Also, it's very easy to apply Futamura results for equations of such type. It's especially third Futamura projection because it makes sense. It sounds like Holy Grail in computer science because it's for any AGI system. This program returns a very special program which maps declarative knowledge to imperative. It's very interesting. But last words about some speculations about these results and future work. If we replace a problem description to informal assumptions, we can obtain many intelligent systems as shown on the slide. We can build a tower of AI programs by inclusion. In this equation, inclusion means that every problem that can be solved by left-hand side also can be solved by right-hand side, but not vice versa. This tower can be constructed by using following system of equation. We can rewrite this in more symmetric form. Formally, this tower can be finite and can be closed by, for example, universal intelligence on the right side. Therefore, it may be considered as a bridge from universal but computable theory to cognitive architectures, for example. It means it's some kind of formalization of top-down approach to AGI. But to be honest, I believe that we need to develop more sophisticated methods of partial evaluation compared with existing now to apply it successfully to such problems like universal induction. I think that's all. Thank you. Questions?
Yeah, so it's interesting. You mentioned some about Turchin's old results. So in the late 90s, when Turchin lived in New York, I worked with him on supercompilation.
Yeah.
We had a Java supercompiler, which did partial evaluation, program specialization, and more. And it was quite funny. I went to IBM to try to sell them Turchin's supercompiler, which could supercompile FFT, various mathematical code.
Yeah.
And IBM wouldn't do a deal with us because they didn't believe it. They looked at it like, well, no, we can't believe you can supercompile this Java code. It must be a fake of some kind.
Yeah.
Because it was way beyond what their team was doing at that time. But and I'm sure what you're doing now is beyond that, because this was 15 years ago. But so at that time, when I was working with Turchin and Andrei and Arkady Klimov on the supercompilation, I mean, we could supercompile, I mean, long programs if they were mathematical code, right? But if you had complex code which, say, did a lot of garbage collection and a lot of memory and managed multiple threads and so forth, their supercompiler wasn't really much use. And it turned out that in the AGI code we're dealing with, it's not so much like tight loops of math computation. Most of the time involved, say in OpenCog, almost all the time is putting stuff in and out of the item space rather than like a numerical analysis type code. So the question is, at what point do you really think these global program optimization methods are going to be useful on, say, something like the expensive parts of an OpenCog system rather than on mathematical type problems?
Okay, it's a very good question. It's really true because there is no killing application in supercompilation or specialization right now. I think that many things depend on choosing of appropriate programming language at first. I think that usual object-oriented language is not very good for these purposes, and I think that we need to develop some special methods of partial evaluation and specialization for AGI programs.
I could tell you what I thought was the killer application for this stuff when I was doing this 15 years ago, which still no one has done, which is not AGI, but like, you know, numerical recipes, like libraries of numerical analysis routines. Those can be specialized based on their inputs to be, we were getting them like 100 times faster by program specialization. So I think that, I'm still waiting for someone to come out with a numerical library based on supercompilation.
The real problem is that if if I want to use a partial evaluator or supercompiler, I need to write by myself because I can't use a supercompiler or other meta program written by something else because it's very difficult to use. Only person who write program
I
usually
tried,
can use this program as well.
Well, my main problem was the code comments were all in Russian, so I got fed up quickly.
Yeah.
But you can
It's
handle
possible,
that.
yeah.
But no, you're right. It's complex code and it's difficult work.
But I really believe it's it makes sense in AGI.
Yeah, so the AGI application that I was thinking of when I was working with these guys was, I mean, in our Moses system, we do some very simple reduction to a simpler form. Of course, this is
something like that.
It's a much more awesome way of reducing programs to a simpler form. And in general, if you've learned a procedure for doing something by some automated reasoning method, you can learn it without thinking about efficiency. Just your automated reasoning engine can think about how to do the problem. And then if you've specified a way to do the problem, then in theory, these kinds of super compilation related methods can turn them into a fast way to do the problem. And
it's called
exciting.
KMP test. It's very famous. How to produce from naive pattern matching Knut-Morris-Pratt algorithm by using supercompilation. It's a very famous.
My favorite example, we had the Einstein fish puzzle, which is a logic problem. We fed a program for solving the Einstein fish puzzle to the supercompiler. It rewrote it globally into a program that just printed out the answer. So the supercompiler solved the logic problem. That was the simplest program. Right?
Yeah, you can use supercompiler for automatic theorem prover as well.
Yeah.
Okay, please.
More questions?
Yeah, please. No? No? Okay, any more? Any more questions? Okay, thank you very much. Yeah, okay.